For 120 years, the automotive industry has been haunted by a ghost. It is a concept so theoretically perfect that Ferdinand Porsche built it in 1900. It is an engineering solution that eliminates transmission losses, deletes the gearbox, and promises pure, direct power. And yet, for over a century, every attempt to bring it to mass production failed. The killer was always the same: physics. Specifically, a phenomenon known as unsprung mass. It turned promising prototypes into undrivable disasters. From Michelin's active wheel to Protean Electric's hub motors, brilliant engineers got close, but never close enough for the assembly line. The mainstream industry declared the technology impractical, a solution in search of a problem it couldn't survive. Until 2021. In a small facility in Munich, a team of veterans from major auto giants decided to rethink the problem from first principles. They didn't just tweak the design, they inverted it. Now, BMW is testing whether these engineers have finally cracked the code. They haven't just built a new motor, they are attempting to reinvent the wheel. To understand the solution, you must first understand the inefficiency. Look beneath the skin of any modern electric vehicle, even the flagships, and you will find mechanical compromise. A standard EV motor sits in the chassis, sending power through a gearbox, a differential, CV joints, and drive shafts before it ever reaches the road. It is a gauntlet of friction. Even in the most efficient systems, between 5 and 15% of the battery's energy is consumed by these mechanical intermediaries before it moves the car a single inch. In less optimized designs, losses can climb higher. It isn't catastrophic, but it is significant, and entirely eliminable. The fix seems obvious. Place the motor inside the wheel. Direct drive. Minimal transmission loss. But historically, this elegant solution created a brutal side effect: unsprung mass. In a car, everything below the suspension, the tire, the brake, the wheel, takes the full violence of the road. If you bolt a heavy motor to that wheel, the suspension cannot cope. The ride becomes punishing. Handling degrades, tire wear accelerates. It is the automotive equivalent of trying to run a marathon in concrete boots. To make an in-wheel motor viable for production, it needs to be powerful enough to move a car, but light enough to float over bumps. For decades, that equation wouldn't balance. Enter Dr. Alexander Rosen and the team at Deep Drive. They realized that to solve the weight problem, they had to abandon the standard motor architecture that had dominated for a century. Standard motors use one rotor spinning inside a stationary stator. Deep Drive asked a deceptively simple question: why not two? Their innovation is a dual rotor topology. A central stator is sandwiched between an inner rotor and an outer rotor, both spinning in precise synchronization. This doubles the active surface area for magnetic interaction. It essentially allows two motors to occupy the space of one. The result is exceptional torque density from a compact package. Consider the comparison carefully. A Bugatti Chiron's engine produces 1,600 Newton-meters of torque at the crankshaft before its gearbox multiplies that force. The Deep Drive unit, according to the company's specifications, produces up to 2,000 Newton-meters directly at the wheel. It's not a like-for-like comparison, but it illustrates the point. This is serious, usable power from a remarkably small package. The entire unit, including the integrated inverter, weighs approximately 34 kilograms, roughly 75 pounds of machinery delivering supercar-level wheel torque. But the dual rotor was only half the battle. To make it survive the road, they had to rethink the motor's internal structure. Traditional motors rely on a heavy iron yoke to support the structure and guide magnetic fields. It is necessary weight. Deep Drive sought to eliminate it. But without that iron spine, how do you prevent the motor from warping under its own magnetic forces? The answer, according to their engineering team, lies in a proprietary copper architecture. They don't use wound wire. They use rigid copper bars, arranged in a geometric truss pattern similar to a suspension bridge. This design serves a triple function. It conducts electricity. It structurally reinforces the motor against twisting forces. And it acts as a thermal highway, wicking heat away from the core toward the housing.
By making the copper perform structural work, they reduce the need for iron. Deep drive claims the implications are significant: up to 80% less iron and approximately 50% fewer rare earth magnets compared to conventional designs. If those figures hold in production, it means a motor that is lighter, potentially more durable, and less dependent on volatile supply chains.
But even at 34 kilograms, adding any weight to a wheel is a calculated risk. This is where Deep Drive partnered with an established giant, Continental. Together, they rebalanced the unsprung mass equation. They integrated a simplified braking system directly into the motor housing and, crucially, they targeted the rear axle first. By utilizing the motor's substantial regenerative braking capability for the majority of routine deceleration events, particularly in urban driving, they could significantly reduce the size and weight of conventional hydraulic components. To be clear, this doesn't eliminate friction brakes entirely. High-speed emergency stops, steep descents, and brake system redundancy still demand conventional hardware. But for everyday driving, the stop-and-go of city traffic, regenerative braking handles the bulk of the work. The calculation becomes a trade rather than pure addition. You reduce heavy mechanical brake components and replace some of that mass with the motor. The net penalty to unsprung mass? According to Deep Drive's testing, it approaches parity. The ride remains manageable. The old curse is weakened, if not entirely broken. In the automotive world, startups make PowerPoint presentations. They rarely make production-ready parts, and they almost never get invited inside the gates of a company like BMW. BMW is known for its engineering rigor. They do not publicly test unproven technology without extensive internal validation. Yet, in July 2024, something unusual happened. BMW announced field trials of deep drive motors in actual prototype vehicles. According to BMW, the initial data was encouraging. The prototypes didn't just survive their testing protocols, they reportedly exceeded BMW's specifications in key metrics. The company cited approximately 20% higher efficiency than current drivetrains and roughly 30% lower cost per newton-meter of torque. But this is a field trial, not a production announcement. The gulf between promising prototype and mass-market vehicle has swallowed countless technologies. BMW is evaluating, not committing, and significant questions remain. An in-wheel motor lives in the harshest environment on the vehicle: road salt, standing water, potholes, debris impacts. Can the sealing and protection systems survive a decade of real-world punishment? Thermal management presents another challenge. Brakes generate enormous heat during sustained use. Mountain descents, track driving, towing. Can a motor sharing that space dissipate heat effectively under extreme conditions? And then there's redundancy. If a traditional car loses its engine, it coasts to a stop. If an in-wheel motor fails catastrophically at highway speed, what happens? These are solvable engineering problems, but they are not solved by a press release. Deep Drive is also not alone in this race. Elaf, a Slovenian company, has been developing in-wheel motors for over a decade. Protean Electric has deployed systems in commercial vehicles. The Chinese manufacturer Zhejiang VIE has shipped units. The question isn't whether in-wheel motors can work, it's whether anyone can make them work reliably and affordably at massive scale. For 120 years, the in-wheel motor has been a ghost story, a perfect idea that reality wouldn't permit. Ferdinand Porsche built one in 1900. Engineers have been trying to resurrect it ever since. What makes Deep Drive's approach different isn't a single breakthrough, it's a combination. The dual rotor topology for power density, the structural copper for weight savings, the Continental partnership for brake integration, and the strategic focus on the rear axle, where the physics are more forgiving. Whether this particular combination will succeed where others have struggled remains to be proven, not in a lab, but on roads, in weather, over years, across millions of miles. The technology must survive accountants as well as engineers. But in a small building in Munich, the ghost has been given new life. BMW is watching. Continental is invested. The data, so far, is promising. Ferdinand Porsche's original vision, a motor in every wheel, direct power, elegant simplicity, may finally be within reach. Not because the physics changed, but because the engineering finally caught up. The Munich Protocol isn't a guaranteed revolution. It is a wager, a calculated bet that 120 years of failure have finally taught us enough to succeed. The ghost is stirring. Whether it walks among the living will be decided not by press releases, but by production lines.